atoms in a molecule do not remain in fixed relative positions but vibrate about some equilibrium position. In this class, we will be discussing the energy spectrum of a molecule undergoing vibrational motion alone, and then discuss the case of a molecule undergoing vibration and rotation simultaneously. When atoms combine to form a molecule, its bond length is determined by the repulsive and attractive forces acting on them. There will be repulsive forces between the positively charged nuclei of both atoms and also between the negatively charged electron clouds. However, there will be attractive forces between the nucleus of the one atom and the electron cloud of the other, and vice versa. The two atoms settle at a mean internuclear distance such that these forces are just balanced and the total energy of the whole system is a minimum. This internuclear distance is called the equilibrium distance or the bond length. If we then try to squeeze the atoms closer, it will cause the repulsive forces to rise sharply. If we try to pull apart the atoms, pulling will be resisted by the attractive forces. The restoring force acting during the compression and extension of a bond is given by the Hooke's law, F equal to minus K into R minus R equilibrium, where K is the force constant and R is the internuclear distance at any instant, and R equilibrium is the equilibrium internuclear distance. Because of this restoring force acting on the atoms will execute some vibrational motion about its equilibrium position. Potential energy of the corresponding motion is parabolic and is given by the expression half K into R minus R equilibrium mod square. If the amplitude of vibrational motion is less, this vibrating molecule can be modeled as a simple harmonic oscillator. We have already discussed the eigenvalues and eigenfunctions of a simple harmonic oscillator in quantum mechanics class. Energy eigenvalue of this system is given by EV equal to V plus half H cross omega with V equal to 0, 1, 2, 3, etc. Instead of the quantum number n we used in quantum mechanics problems, here we use the vibrational quantum number V, which is commonly used in spectroscopy. Also, we specify here that the frequency is the oscillation frequency of the molecule. We use this subscript in spectroscopy to ensure that this is the vibrational frequency of the molecule, not the rotational frequency. This vibrational frequency is given by the classical expression square root of K by mu, where mu is the reduced mass of the system. This equation gives the energy in joules, and hence we have to divide this expression by Hc to convert this energy into wave number. Then we get energy in wave numbers as V plus half omega Sc bar, where omega Sc bar is given by oscillation frequency divided by 2 pi c, where c is the velocity of light expressed in centimeter per second. Since the quantum number p can have only integer values, it is clear that the vibrational energy of the molecule is quantized with equal separation between the levels. Also, it is clear that a molecule can never have zero vibrational energy, since the lowest possible energy corresponding to the lowest value of vibrational quantum number is not zero. It implies that the atoms can never be at complete rest. This lowest possible energy half omega oscillation bar is known as the zero point energy. As in the case of rotational spectra, vibrational spectra are observed with molecules with permanent dipole moment. Hence, only heteronuclear molecules like HCl shows vibrational spectra. The selection rule for transitions between various vibrational energy levels of the molecule is given by delta V equal to plus or minus 1. From this, we can find out the energy change involved in the transition from one vibrational level to the next level, V plus 1, as omega oscillation bar centimeter in width. Therefore, the spectral line corresponding to the transitions from any vibrational level to the immediate neighbor level will give a single absorption or emission line at omega oscillation bar centimeter in width. As these wave numbers corresponds to the infrared region of the electromagnetic spectrum, it is also known as infrared spectrum. Remember, we get this kind of spectrum on the assumption that oscillating molecule executes simple harmonic motion. This is a good approximation for very small amplitudes of oscillation. Real molecules do not execute simple harmonic motion exactly, as real bonds are not so homogeneous. If the bond between the atoms is stretched, there comes a point at which it will break. That is, the molecule break into atoms. Energy curve for a real diatomic molecule looks like this. This dotted line represents the potential energy curve that we expect if the molecule is performing simple harmonic motion, and this solid line is the real potential energy of the real molecule. P.M. Morse gave an empirical expression known as Morse function, which fits this curve to a good approximation. And here in this Morse function, this D equilibrium is the dissociation energy, and A is a constant for a particular molecule. If we use this potential energy function in place of half kr minus r equilibrium square in the Schrodinger equation, then the allowed vibrational energy levels becomes like this: V plus half omega E bar minus V plus half whole square omega E bar Xc. Here Xc is called the unharmonicity constant, which is a small positive quantity for stretching vibrations. To know what is omega E bar, let's rearrange this equation like this. If we compare this with the energy levels of harmonic oscillator, you can see that omega oscillation bar corresponds to omega E into 1 minus Xc into V plus half. That means omega E bar corresponds to the oscillation frequency of the anharmonic oscillator, or in other words, anharmonic oscillator behave like the harmonic oscillator but with a frequency which is decreased steadily with increasing the quantum number V. If we consider a hypothetical energy state with V is equal to minus half, we get omega oscillation bar equal to omega E bar. Thus, omega E bar can be considered as the equilibrium oscillation frequency of the anharmonic system. The selection rules for the anharmonic oscillator are given by delta V equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. Thus, unlike the case of harmonic oscillator, it is possible to have transitions to higher vibrational levels also. However, the probability of such higher order transitions are very less. The spacing between the vibrational energy levels are of the order of 10 to the power 3 centimeter inverse. Hence, the population of V equal to 1 state at room temperature can be estimated using this Boltzmann distribution. And this calculation shows us that the population of the first vibrational level is much less than that of the ground state level. Thus, we can ignore all transitions originating from V equal to 1 or above states. This figure shows the allowed vibrational energy levels and some transitions corresponding to delta V equal to +1, +2 and +3 from the ground state for an anharmonic oscillator. Energy change involved in the transition from V equal to 0 to V equal to 1 state is given by omega, can be calculated from the energy difference of these two levels, and it is given by omega E bar into 1 minus 2 xe centimeter inverse. Similarly, we can prove that the energy change involved in the transition from V equal to 0 to V equal to 2 state is 2 omega E bar into 1 minus 3 xe centimeter inverse, and from V equal to 0 to V equal to 3 is 3 omega E bar into 1 minus 4 xe centimeter inverse. These three transitions are shown in this spectrum. Since the value of anharmonicity constant is very small, these spectral lines are very close to omega E bar, 2 omega E bar and 3 omega E bar centimeter inverse. This line corresponding to V equal to 0 to V equal to 1 is called the fundamental absorption, and this second line is called the first overtone, and the third one is called the second overtone. Even though we have seen that the population of V equal to 1 or other higher states have a small fraction of the ground state population at room temperature, the situation can be different at a higher temperatures. For example, at 600 Kelvin, we can see that the population of V equal to 1 state can be close to around 10% of the ground state population. Hence, transitions from V equal to 1 to V equal to 2 state may also lead to a spectral line with intensity approximately 10% of that of the fundamental absorption. The energy change involved in this transition is given by the energy difference between the second and first quantum state, and that is given by omega E bar into 1 minus 4 xe centimeter inverse. Thus, this weak absorption line appears very close to and at a slightly lower wave number than the fundamental line. Such bands are called hot bands, as this line appears only at higher temperatures.